Hello everyone, welcome to this research seminar. Today we are excited to host Johannes and Nino, a research scientist at Google Parallels of Intelligence team in Zurich. Their work focuses on rethinking foundational assumptions in AI, and today they'll be presenting MesaNet sequence modeling by locally optimal test and training. I'll hand it over to you. Please get started.
Can you hear me? Is it good?
Yeah, it's good.
Yeah. So thank you, Songlin, for inviting us. It's a super pleasure to present the work in this great seminar. Yeah, this has been like a paper we have been working on in the last months, and has been really joint work with an amazing team. So as Songlin already said, we are based in Zurich, working in a new research team at Google, trying to push the frontiers of current or change the current paradigms of AI. And yeah, so there have been like long-term collaborators of mine, and Nino, Max, and Sejin. And also we have been working with Songlin for the first time, which was a real pleasure, and Joao and Luca, and many others. Okay, so the talk, we separated the talk actually in two parts. So there's a first part which kind of gives a little bit of a background story on why we were working on this kind of new recurrent neural network layer and model. Then in the second part, we will discuss how the MesaNet kind of looks like, and present some results on language modeling. Okay, so I start with the first part, and then second part will be mainly take over from Nino. And so, yeah, like the first kind of thing that made us curious about LLMs actually was like the great paper, GPT-3 paper from Brown et al., where they showed this amazing capability of LLMs to learn in context. So what that means is you present like a couple of examples in context of a language model, and without any parameter updates, it seems to learn this kind of tasks based on this task description that you give, learn this task in context. So you see a couple of examples: addition, I don't know, fixed spelling mistakes, and translation. Like our first kind of motivation was to understand what is going on here. So why can language models actually do this? And the second motivation was then, which we'll see later, kind of based on our understanding and insights, build like a new sequence model that is hopefully better at in-context learning, and we will see if we succeeded at that. But yeah, like in-context learning was our main motivation, understanding and designing new sequence models that can do this better. And so what we started with is a super simple autoregressive toy model. So this was inspired by a couple of other papers that studied in-context learning and in more toyish settings. So you don't train your transformer model on language, but actually on continuous data. And so we built our work on this and create sequences from very simple kind of generative models. So you have something like H1, which is just an initial state. And then you, given this initial state, you push forward a sequence model, a simple sequence model here, which is potentially has a nonlinear function transformation of the state, and then an A matrix, which you reply iteratively to this transformation of your state, which gives you your next hidden state. So this is a very simple recurrent neural network, if you will, and we just perturb it a little bit with noise. And then what you do is that you actually observe ST, which is a potentially low-dimensional observation, partial observability. So this is a partial observable system. So the C matrix and this A matrix are, which is important here, are new for every sequence. So you need to predict the next observation, ST, somewhat infer in your transformer model these matrices. And so this is exactly what you do. You present the transformer with a sequence, and you try to predict, given the last ST and the context, you try to predict the next ST+1, which is like this partial observed part of your sequence. And you train this on the next token or next continuous output regression loss, and you do this over many, many sequences that you obtain by sampling also different ANC matrices. And so what we found is that if you inspect this toy model, so you now train a transformer with a couple of layers, where you see that the transformer, if you look at the next token MSE, so the arrow that you train the model on, that after a certain number of tokens, the model is really well able to predict this next token. And this gets better if you have a deeper model. So the depth of the model really helps you to bring down this arrow to 0. And we don't have this in the legend, but this yellow dotted line here is kind of the optimal thing that you can do, which is actually the Mesa layer, but we will come to this later on. And so now what you can do is you can actually look at the weights of this toy model. So you trained your transformer model, and interestingly, you will see very, very structured weights. And this somehow suggests that your transformer is not somehow remembering like all the ANC matrices that you obtained during training, but actually implements somewhat of an algorithmic solution to this problem. And another kind of interesting finding is that what happens is that you can train a linear probe on the hidden representations or the residual stream of your transformer, and actually can read out the last STs of your sequence. And this prediction, like this probing, becomes more and more good if you have a wider residual stream. So the more you can actually copy into this residual stream. So this is very related to this induction head, as we say below here, very related to this induction head mechanism from Olsen et al. So this super nice finding from Anthropic that you copy over tokens that were previously seen in the sequence. You copy these in your residual stream. And if you give more and more capacity in the residual stream, the model tends to do this more and more. And you can kind of train linear probes to do so and find out that this is happening. And so basically our hypothesis is that the transformers solve this task by first copying over previous seen parts of your sequence, which are partially observed from the generative model. And then what you do is you actually take these Zs, which are concatenations of these previously seen STs, and you train a linear model within the depth of your transformer to predict the next Z. And part of that next Z is actually your next ST, which you see. And the more you copy over, the more you can get rid of this partial observability. So we have some theory on this in the paper if you're more interested. But the important thing is that, which will also become important later on, is that the model is able to actually solve this least squares regression problem in somewhat an optimal way down the layers of the neural network. So we have an hypothesis and a couple of propositions how the model can do this, and actually show the next slide that the transformer will do this. But the important insight is that we kind of hypothesize that the transformer model is able to do this for all time steps t actually in parallel. So there's a mechanism to solve this problem for many time steps in parallel, very efficient way, and which was super important to understand from a kind of different perspective, how you can do this in parallel, basically by reverse engineering this algorithm outside of transformer weights. So the important insight for the Mesa layer later on is that you can actually compute this precondition matrix times Z, which is actually an inverse of this ZT transpose plus the regularization term, where ZT is the concatenation of all your previous ZTs. And you can compute this inverse times your current ZT. So you can approximate a solution to this linear systems of equation actually in parallel for many time steps. And we show one particular way. We will use a different way later on the Mesa layer. But in our previous work, we discussed a way to use Newton-Schultz to do this in an accelerated fashion. And once you have that, once you have this preconditioned Z, you can actually solve this problem by a single gradient step of this loss, given you already preconditioned your Z. So it's kind of a three-way algorithm that the transformer is doing. First, it's copying over the STs to obtain these ZTs to get rid of the partial observability. Then you actually approximately precondition your ZT and solve with a final gradient step, kind of this least squares problem for many T's in parallel. And so there's some evidence for this theory in the pre-trained, like in these transformers, if you pre-train them on this toy model. So what you can do is actually probe for the preconditioned ZT in the residual stream. So again, have like these linear probes and show that down the layers of your neural network, of your transformers, you can better and better read out linearly these preconditioned ZTs. And you can also compare the solutions of the transformer versus our proposition, which is based on this accelerated Newton-Schultz algorithm. You can actually compare the solutions found by a 3-layer transformer or a 7-layer transformer, compare it to like our proposition. So the theoretical model fits the trained model quite well here. And then you can also, if you use like a nonlinear transformation of your model, can actually find and probe again these nonlinear transformations that we had in the generative model. If you remember, we can also like transform our hidden state first linearly before computing the next time step. You can actually probe for these also very well in early layers of your network. Like another interesting like finding was that, and then we'll continue with the Mesa layer. Like another interesting finding was that you can actually now use this autoregressively trained transformer, which just purely predicts like next token in these toy sequences. You can actually kind of use it to solve, let's say, linear regression problems where only where you present the model, not these ST elements of the sequence, but actually XY pairs from a linear regression problem. And the transformer is able to solve these quite well. So kind of this algorithm that the transformer is kind of implementing inside its weights can also be leveraged later on to kind of be used as a few-shot learner, if you will. So kind of mimicking this finding of LLMs. So just the next token prediction will also make you, let's say, a good few-shot learner in this toy model, which was kind of cool. Okay, so basically, just to recap, what we tried is to understand theoretically, or let's say in a toy model, and understand like a little bit from mechanistic interpretability tools, like what transformers do when you train them on really these toy models, if you can recover these capabilities of being a few-shot learner. The important insight was this: through this mechanistic understanding how the transformer kind of worked, we got to an algorithm that we will now scale up to language modeling, meaning that we were able to understand how to compute these least squares solution of the problem for many time steps T in parallel. Like another interesting finding is that what we did is here that we trained on, it's basically like we sample many of these sequences that we train on in an online fashion, so you never see the same data twice. And there's a super interesting paper from Raventos et al. That actually look at what happens if you fix the number of these A and C matrices, and find that actually like quite a low number of these generator matrices are needed to obtain this algorithmic solution. Okay, so after that first origin, like story of the Mesa layer, based on this mechanistic understanding and based on the kind of motivation to understand in context learning and potentially find like a model that can do better in context learning, we now come to the MesaNet. Basically what we do is we follow the transformer architecture and many other important works, gated linear self-attention, DeltaNet, XLSTM. They all use, I think most of them use like the classical kind of backbone. So basically what you do is you stack these local learners. So now the question is, when you stack these local learners, you tie these Mesa layers together. What will happen? So yeah, our finding motivate these neural sequence models that are at every layer these local learners. And each layer, so outer gradient descent provides each layer with a local learning problem which it solves, and the MLPs, as in the transformer, interconnect many of such layers. And so yeah, this has really interesting also connections to a field like fields in computational neuroscience, in which we worked also quite a bit in, where we want to understand how credit assignment, how, let's say, gradient descent could be happening in the brain. And it is kind of believed that backpropagation is not such an algorithm which the brain uses to learn and changes synaptic weights, but there are many different kind of algorithms developed and ideas here. And somewhat interestingly, there are connections to works where you have a deep neural network and you actually just locally train to fit your targets, which in certain circumstances actually works quite well. So there are these layer designs also have like super nice and interesting connection to ways to get rid of backpropagation, to change the weights of your neural network and actually apply these local learners. Yeah, I don't think I need to say much about this. So here's just a quick recap of softmax self-attention. The interesting part is that softmax is pretty flexible in kind of allocating a compute and memory. So with growing time, compute and memory cost grows linearly. So you store basically everything, all the text and all representations at every layer are stored. If you do this naively, of course, and therefore it becomes quite costly. And so there's been many works on changing the softmax equation by dropping it, and basically therefore you obtain not constant, not linear growing memory and compute cost, but actually constant by realizing that you're updating this fast weight matrix, which is these outer products of values and keys here, which we denote as phi t. And with time, you update always this matrix with a rank 1 matrix, the outer product of the new k and b, and you query this so you could produce an output of this layer by querying the fast weights. Yeah, it goes without saying that this is a model already developed by Schmidt-Huber in the beginning of 90s and kind of rediscovered in the current era of transformers. And so there's a beautiful kind of associative memory view of this. So when you talk about memories, you can store certain number of key value associations in this matrix. And there has been interesting extensions of this based on the success of softmax, designing these let's say called modern Hopfield networks. And so yeah, just to highlight that there's a nice memory view of these models. And another view of these models, which the Mesa layer also is part of, is this of local learning. So this is a nice paper, like kind of provides this framework for all these layers from Wang et al., where you over time collect Ks and Vs, and then you have a function MT, which is based on these KVs and your Q to produce an output. And so basically you frame this as a memorization problem during test time. And you can view basically all, with a few exceptions, I think, basically all kind of softmix self-attention alternatives and also softmix out of this. And the Mesa layer is here classified as this parametric version via exact solution. And yeah, Song Lin wrote nicely on her Twitter that Mesa versus DeltaNet is roughly analogous to recursive least squares versus least mean squares in the signal processing literature. So making MesaNet the more powerful of the two. So we will see if this is true. But yeah, so there are these very nice connections to classic, if you call signal processing literature, or just generally like machine learning literature that tries to find solutions to these memorization problems. But I think what is interesting to note here is that like we come more from this point of view of trying to improve in context learning. So it's a little bit more about this generalization idea of learning in context to predict like the next token. But of course, memorization is part of that. Yeah, here's a quick overview of all these models that have been developed. Yeah, like a kind of a disclaimer, here's the MesaNet. So kind of extending a bit like the complexity of these equations here. Yeah, so as we already alluded to in the previous slide, like the Mesa layer is now extremely close to this original least squares problem over time, which we also wanted to solve in this toy model of in-context learning or autoregressive sequence modeling, where you optimize a phi. So you really try to find the argument of the following least squares laws, where you penalize the different terms with the gamma term. So this is this forgetting term that the literature also found to be important for previous models. So you also have a way to forget the past based on a time dependent, so residual connection dependent gamma term. And so this is basically a hardwired model layer that follows the recipe that we kind of discovered in these toy transformers that we trained. And yeah, again, like this forgetting factor determines how strongly this association is learned and retrained. So to kind of show how we solve this in practice is, so we have the layer now not only has like a single state matrix, but actually two. So the first state matrix is extremely similar to gated linear self-attention. So you have a state GT that you update or which you partly forget with YT, and then you have an input gate that determines how much you update, like how much you write the new VK association into the state. And then we have an interesting second state, HT, which does the same, but actually just with KT transpose. And you can show that actually what you need to do is that if you want to obtain phi t, you compute phi t with Q. But this is the same as actually now expressing this in the GT, HT with GT and HT matrices, where GT is again defined here above, which is actually multiplied by this precondition QT. And so if you apply this Lin solve, what you do is you kind of find the QT star such that if you multiply this with this matrix, you obtain GT, which is actually exactly the solution as if you would compute the inverse of HT plus lambda identity with your QT. Actually, here we can, so this identity is actually like a diagonal matrix where we have potentially different lambdas on the diagonal here. And so the interesting part of this, especially when it comes to parallelized computation, is this lint-solve. So this looks super scary, but we will solve this in a bit. So just to, because we have this kind of recursive update of the Mesa layer. So this is how you would potentially do it during inference. You can also, as you probably all well know, you can also view these operations in matrix form. So here's the classic matrix form of softmax. You can also view a linearized softmax, so gated linear self-attention and so on, as in matrix form, which already alludes to the fact that you compute the output for many t's. You can compute the output for many t's in parallel. And now we look at how you can do this for the Mesa. So actually, the Mesa is exactly the computation of gated linear self-attention, where we replace Q. So basically just this linear transformation of your residual stream with Q star. And Q star, like the matrix Q star, consists of many of these QT stars, which are the solutions to this linear systems of equations in parallel. And now we quickly look at how you compute this in an approximate form with a conjugate gradient method. And so I wrote here, wrote here like a kind of weird form of the conjugate gradient method. But the important thing is that that the conjugate gradient method, the heavy lifting of the conjugate gradient method, are actually matrix vector products. So this HT is this KK transpose matrix, so that we kind of defined previously, which you during inference update and time, plus the regularization terms times the search direction. So this is the search direction that you kind of update in your conjugate gradient method. So all the details don't really matter, and you can easily understand them, I think, if you look in the appendix. But the important thing is that the heavy lifting of this updating of the search direction is actually equivalent to the GLA computation. So this part here, which is this outer products of k vectors times some other vector, is equivalent to a GLA computation, for which we have, for Songlin and colleagues, provided extremely fast parallel ways in Triton to compute these in an extremely efficient manner. So basically, what the Mesa layer kind of end up with is just repeating GLA computation many times. Just a small attention here. So numerics in this are problematic, and we will kind of discuss this later. But like these iterative methods tend to be numerically unstable. So this is a point of caution here. And so the interesting part is that the Mesa layer is simply computationally just simply consists of running many steps of GLA, depending on how well you want to approximate this linear systems of equation solution. So you can run this. So this boils down to running many steps of GLA, and then doing a final GLA step to actually compute the output of the layer for many time steps in parallel. And so here you see like one of the throughput, one of the speed figures that we provided in the paper, and you see that for equivalent architectures, depending on how many conjugate gradient steps you do, actually the Mesa layer performs quite competitively with layers like gated delta net and GLA. And yeah, you can see here also like this nice or this expected throughput aggregation of the transformer when you increase sequence length. And another interesting fact about the Mesa layer is this dynamic test time compute allocation. So if you look at the conjugate gradient method, you cannot only just use like 30 gradient steps as we did in the figure before, but actually stop the iteration once you improved the error to the fixed point of this solution to a certain percentage, and then you just stop. And so we will see later in language modeling what this kind of means. But so based on this epsilon term that you can set, you will finish computation of the Mesa layer earlier, potentially earlier and this is data. So the interesting fact is that this is data dependent. So once you set this epsilon, potentially for some tokens, after like a couple of gradients, conjugate gradient steps, you might converge, while for other tokens in your sequence, you need many, many more steps to converge. And so there's just interesting parallels to softmax and RNNs, like parallels and differences, where softmax just data independently just increases compute and memory. The Mesa layer tends to have, well, constant memory as other RNNs, but allocate compute dynamically based on this epsilon that you set, and kind of the convergence rate of the conjugate gradient method, depending on the data on the sequence that you provide. Okay, and so just to come back to like what you do with a layer, we just follow like super standard transformer architecture and replace. So we have a residual block which we repeat like n times, and instead of using multi-head attention or any other of, so we tested the Mesa against XLSTM Mamba 2 DeltaNet and Hawk, but this one is like a little bit outside the architecture of these other variants. So what you do is you do this linear projection, you apply convolution and some nonlinearity, you normalize usually KQ, and V, and you just apply a sequence mixing rule. So we really wanted to see if you one-to-one use the same architecture and just change this mixing rule where you naively can just use MHA, XLSTM, Mamba, and so on, and including, of course, the Mesa. What happens with your model if you train on next token prediction, and especially on downstream performance. Okay, so now I will give the computer to Nina.
Thanks. So as the last part of the presentation, we're going to look at quite a lot of evaluations. And like we decided to first start with as a synthetic evaluation environment where we use synthetic generated data by the MENT benchmark and the REC benchmark, which are like really cool benchmark to test novel architectures and their context learning ability. And basically, this is then like synthetic evals based on as a distribution of the data which we can control for. And so what we started with is the MET benchmark, which is basically simple, like a bunch of different tasks, like in context recall, clean, noisy, and as a fuzzy versions, like selective copying tasks, compression, and memorization. And like for all the models which we're going to evaluate, like we use a fixed two-layer model architecture, sweep over optimization parameters, and then report the best according to the benchmark as a protocol. So the interesting thing to see here is, like as expected, the MesaNet performs quite strong on the MET benchmark. And there is also a second layer, which we present here, which we call the Hawk as a MesaNet layer, which is simply as hybridization of the Hawk layer and the MesaNet. And the interesting thing is also, like, if you look closer at the results, that you can kind of do a bit performance arithmetic by combining the two layers. For example, if you look closely here at the compression as a signal, you see that Hawk is quite a powerful layer here, and is outperforming the MesaNet here. But once you combine the two layers together, you get even a further boost in as a performance. And we see this also for a range of other as a benchmarks. And also what's nice to see is like we can outperform the transformer on the MET benchmark on quite many as settings. So showing that the MesaNet has quite something to offer. So then as a next step, we move on to the as REC bench by AccuREC and AL. And what we basically do is, so you have a set of probabilistic finite automata, which you synthetically as a generate, you train your language model on, and then you evaluate under some unseen holdout PFAs to see how well the model is doing. And so what we're doing here in this eval, we always take 1,000 examples during as a training and vary the number of as a DFAs during the training. So the more DFAs you are seeing during training, the easier it should be then to get it right during the as a testing phase. And again, here we see the transformer is performing quite strong, but the MesaNet is like outperforming all the other existing layers and nearly matching the transformer as a baseline. And like for its completeness here, we also use the benchmark as a protocol from the paper to a scan over different embedded layers, have an optimization parameters, and also the best model niche configuration is then as recorded. But the interesting finding is more, and also like what's the biggest motivation was in this project, like scale it up to the language world, like train it on real language data and see if we get the expected gains that we see in the toy experiments, the synthetic benchmarks that we tested on, if we can also find this in the real as a language world. And what we're going to do, we're going to evaluate 145, 450, and closely to one as a B as a model is trained on 2 different amounts of as a data, sweep learning rates for all the models, and use the exact identical data ordering to have a really fair one-to-one comparison of the models. And from an evaluation perspective, we're going to look at Perplexity as reasoning benchmarks in the multiple as a choice form, in context recall benchmarks, and as a few shot. So the interesting thing to start here is like before started, we were quite sure that how we set up the controls and the evaluation baselines is quite a crucial thing to understand what's going on. And the interesting thing is like we all know that linear layers suffer at in context recall if the context is as a large enough. So an interesting question is like how long is really the attention span of these models, or how much information can they as a process? And it's quite interesting in this as a context to look at sliding as a window attention models with a varying as a window as a size, because we can somehow expect perfect recallability within the window, but we have also this constant per token memory and compute cost as a property of the model, which brings them closer to the linear as a models. And the question is then like, how much window size do SVA models really need to be competitive on Perplexity and the benchmarks? And since everyone in the field is basically as hunting Perplexity and trying to get it down as much as possible, we first started to test Perplexity on a set of different benchmarks. And like it's not meant to be as read here the numbers, but as you can see, we did quite an exhaustive scan over different validation sets and quite different model as variations. And if we zoom in more closely on the 1B model trained on 50B tokens, you see quite nicely here that MesaNet is performing quite strong, but the hybridization with the Hawk meta is even as stronger. And the interesting fact is this trend holds across all models as a sizes and number of as a training tokens. But probably the more interesting thing is if we look more closely at the SWA and models, we see the perplexity of a SWA model with a 1K as a window is already pretty close to many of the linear as a models, and even as a better than as a most of the models. So this raises the question, like how much should we really as a trust the perplexity when comparing different architectures, which also have like different inductive biases, like are better at earlier information in the sequence or are better at later information in the sequence. And this as a brought us also by a bit of trend in the community to not look at aggregated perplexity, but break it down with the loss over the token as a position. So we look at the loss at every particular token as a position, but in addition, also compute the delta with respect to the tuned transformer as a baseline. So the interesting thing, which you can see here on the right, is that recurrent models here, where a negative NNL delta means that you're as a better than the transformer, that all recurrent as models are doing better than transformer early in the sequence. But after some time, like you're around like between 512 and 1K tokens, the transformer is outperforming them with respect to the loss on that particular token as a position. The interesting thing is like here you see on the right, if we plot this as a log scale, you see really the ordering of the layers by the Hawk model being the strongest early in the sequence, but it's also deteriorating then quite early in the sequence. So it's really just greedily really good at early tokens in the sequence, but then falling behind later. And then we see kind of the other models, the Hawk as a Mesa, which still benefits from having the Hawk layers inside, and the Mesa layer, get the delta, and all the other layers. And to summarize, like the trends that we see a bit on this 1B scale with 50B tokens is the majority of models have kind of an advantage window up to 256 tokens. And as a Mesa and Hawk Mesa extends then beyond the first 512 as a tokens. And since the Hawk model was beating the Mesa early in the sequence, this was also kind of the motivation why we tried the combination of Hawk and Mesa in a hybridization to see can we kind of use the complementing strengths of both layers to bring them together and get even more as a magic out of the two. So the takeaway a bit from this analysis is the Mesa layer is doing quite well, but it's not able to match the transformer baselines at later sequence position, especially after 1K. And we should probably never solely look at aggregated perplexity as a measures when comparing different model as families, because as we remember, the MesaNet was overall stronger than the transformer, but if we look more closely, we see this mostly coming from being better at the early tokens. So as a second interesting thing, which we also did not really as a highlight here, is like in the main paper, but as this is all in the appendix, if you look then at these different as a model as a sizes and different token as a regimes, you see that these advantage windows of these recurrent models get smaller with more as a tokens. So as you can see here, the indicated line here is always the crossover point when you fall behind the transformer with respect to language modeling performance at the specific token position. And you can see here, this window was always as a shifting with more tokens closer to the beginning. So the advantage gets like smaller compared to what we see on the low token as a regime. But it's, I don't need to say we only ran on as 50B tokens, so it's definitely interesting to see like what happens at 100B token, one as a trillion tokens, for example. Is there some magic at linear layers or these RNN models going on? Like, are they only focusing at later tokens in the sequence at the later part in as a training, where the transformer maybe has an opposite way of when most information is spent on which as a part?
Actually, we have
thing which is also, yeah.
We have a
question.
There was a question.
Yeah, can you read the question first?
Yeah, I'm quickly. Does the transformer here use components such as short convolution, output RMM, as norm like other as models? I think
it's classic. That's this Llama 2 model. There's no short convolutions. What was the other thing?
RMS as a norm.
So you don't normalize the keys and the queries or the values.
Yeah, then we go ahead. And otherwise, like, please feel to interrupt us and ask anything. So the second thing, which is then interesting to check, is like, as usually like one of the benefits that is claimed when you're looking at linear models, like since they use way less compute when going over long as a sequence, so the real benefit really kicks in if we go to long as a sequences. And the generalization to long sequences is something which is discussed quite heavily in the field. So in order to verify this, we also run perplexity evaluations on this long as a context benchmarks, which is as a wiki text, PG19, as a Goff record, reporting some other benchmarks. And as you can see here again, the MesaNet and the Hawk Mesa are performing quite strong. But if we then again remember, like Perplexity may as give us a bit of illusion of as a superiority. So we move on and check the negative log likelihood over the sequence position, but then also compare the mean so far negative log likelihood with respect to the SWA performance. Because as you can see here, a SWA model with a 1K window is already performing quite strongly. But in a SWA model, we also know there is just an attention span of 1K, so it cannot perfectly model all the associations which have been there. And there would be, of course, also cool evaluations metrics like long as a perplexity. I think I saw the author's name also here in the call, which is a really cool paper. You could also use this novel as a sub-composition of perplexity to evaluate how well these models do on as such as a tokens. But when zooming in here again, we see as expected at the 2K window, the drain context window, the transformer baseline is exploding because like we did not adapt them to work longer as a context. And then you see kind of in a staged manner of how some other linear models are exploding after a longer as a context length. And the MesaNet is doing up to 4K tokens quite well, matching closely the GeltaNet performance, but then beyond 4K tokens, GeltaNet is likely as a superior. But the more interesting fact, which we should pay more attention to, if we look at the 0 line, which means the SWA 1K window, is kind of really, really close to the performance of other models. And we see after 16K tokens here, or then here at the last plot, also close to 32K tokens, we see most models cannot compete with a SWA 1K as a model, which really indicates like it's probably a flawed as a measure of really looking just at perplexity or the loss at a particular sequence position, but that we need better as measures to look at how well these models do at longer as a context. And then as a second phase, we were interested in how well do this model and as a downstream benchmarks, especially as a zero-shot common sense reasoning in context recall and as a few-shot learning, where we looked at GPT-2 as a word scrambling tasks and the translation from as a VMT as a suit. So the interesting thing here is, again, let's take our control, the SWA models, and look how well are they doing on as a zero-shot common sense reasoning. And so this result was quite surprising to us. So we knew that these benchmarks are kind of flawed and we have much as a noise in it. And like sometimes these benchmarks are too hard for a model at that scale. So it was really hard to say, like, if we're performing better on the benchmarks, are we really better, or are we just picking up a lot of as a noise in these benchmarks? So when looking closely at this course, you see these 4 benchmarks on the right, which means the Lambda benchmark, Hellas vacancies, race M and race H benchmarks, we see, as expected, performance is increasing with a longer attention as a window. And usually the transformer is kind of the best performance. Sometimes a SWA 1K or 1500 range window is getting quite close or a bit better, but this can be probably also attributed to noise or being benchmark based, because like probably most information lies within as a shorter amount of tokens. But on the right, you can see surprisingly that the SWA S16 model or SWA 64 models, they outperform the full range transformer quite a lot. And it's also surprising that it does not happen just in one benchmark, but it happens in many as a benchmark. And I do not want to call out these benchmarks as bad, but these benchmarks have been mostly designed to measure the performance on transformer baseline. So you never had these problems to fight with local language modeling versus global language modeling. So there is probably clear bias in these benchmarks. And the other thing is, since it's kind of a multiple choice driven benchmarks, and you compare this possible option against other possible options, there come in quite a lot of biases into play, like the length of the possible length, or are there many key tokens or just a few key tokens, which can all bias the results. So based on this as a finding, to cut a bit through the noise and look not in every score in detail, we started to split benchmarks into this global benchmark split, which are all benchmarks that benefit from longer context as ranges, and then the local benchmarks, which are probably solvable through local heuristics or too hard, or maybe just as a noisy at that particular as a stage. Then in a second step, we looked at the in-context recall benchmarks. We just adopted the paper from the ASA-based paper from ASA24. And here it's also, as expected, benchmark scores are increasing with an increasing as a window, except the squad benchmark, which is a bit an outlier, many things. But the interesting thing is here, once you look closer at these benchmarks and try to analyze where is the relevant token that you try to recall, you see also like these benchmarks are heavily skewed. For example, the FDA benchmark, you see there is this wild jump from a SWA 1K to a full range transformer. And here again, for all the combinations. And when looking closer at the FDA benchmarks, we realize that you mostly try to retrieve information which is part of the header of the as a document. And since the documents are truncated to 2K tokens, you need the full range to see the tokens. So hence it's like really, really hard if you have a limited attention span to retrieve that particular information. And the squad benchmark is a bit the opposite of the as a distribution. So many key tokens are at the later part in the as a sequence, like from the half of the sequence towards the end. So even if you have a limited range, you can still do quite well on these benchmarks compared to other. So given that, we proceed as usual and look at all recall benchmarks together. And then as a lastly, we also look at the few shot performance from these GPT-2 tasks like cycle letters in Word, where it's just the tokens or the letters are permuted and you need to recommute them and checked with as a few shot examples to see how well they do. And the other one is this translation benchmark where we use the blue score to measure translation performance. And here a similar picture than in as recall, you see an increasing performance, especially once you have a couple of as a few shot examples, you see an increasing performance if you have longer as a range in the attention as a window. And given all like this analysis on the SWA models, we jump on now to the comparison of the main models we were interested to, like all the linear models, the transformer, and still show the SWA to contextualize the results a bit. So the interesting thing is in the global benchmark, where we know that you need more range to be as good at the task, or it's beneficial to have longer range to be good at the task, we see that the MesaNet is really doing quite well. It's outperforming all other RNNs and is nearly matching the transformer as a baseline. But on the other hand, on the local task, where we detected that you can even do with an attention window of 4 or 16, do quite well, we see on one hand that all the scores are quite close as together, which means like probably there's quite some noise or these tasks are too hard. And the other surprising thing that the Hawk model, a model which is quite bad at the global reasoning benchmarks, is doing quite well here. And we have again similar findings if we look at the hybridization then, for example, at the Hawk Mesa, we have again the Mesa layer is again weaker than the Hawk Mesa combination, which means like that possibly these complementary strengths are playing out in this benchmark. Then we move on to the in-context recall benchmark, and here we have again very similar findings to the global benchmark as a subset. So the transformers are still unmatched. So also the MesaNet is not able to get close to the transformer with respect to in-context recall, but we see that the MesaNet is doing better than any other linear model RNN that we have evaluated, and you see also these nice performance improvements with the SWA as a models. And then finally, we looked at the word scramble and the translation, which are both as a few shot benchmarks, the 100 shot and the 50 shot as a setting. And for word scramble, we see it's a quite ICL-driven task because it's quite as official, these manipulations. We see the MesaNet is performing quite strong, even outperforming the transformer, and is also better than any other linear model RNN that we as a tester does. And then on the other hand, the translation, which is a task which was revolutionized quite a lot by the transformer through the contextual embeddings that you could get from the model and attention. You see transformers are still way better than any other as a model we as a tested on, but the MesaNet is doing quite well here. But we also need to say like GLA, XLSTM, and gated delta net is performing quite strongly there. And then as a last analysis with respect to the relations, like Johannes presented as a previously, that we can use this conjugate gradient optimization in a dynamic way. So we can allocate dynamically as a test time compute during the inference part. And we have mainly two ways of how we can do this. So we either set uniformly as a step. So we just set a maximum amount of SSCG steps that you can execute is either 4, 5, 6, or up to ASAP30. Or the other thing is we have as a stopping as a criterion that determines when we stop the CG as a method. And the interesting thing is once we have this stopping as a criterion, we see across these three benchmark suites, performance is not varying that much. So even if we have a high stopping criterion or relatively high stopping as a criterion, the models still do quite well. But compared to if we just say you have 0 CG steps, 1, 5 up to ASAP30, we see kind of, again, a linear performance improve the more CG steps we apply. And when looking then closer, what happens, for example, over the sequence length, I think it's explaining then quite a lot of these results. So we here again take the Mesa, which is the normal Mesa version we use with 30 CG steps as a baseline and compute the delta with respect to the ablations. And what we see here, for example, you get quite stable results if you have a optimization as a threshold, as a stopping criterion. So the lower we set the threshold, the closer we match the performance with 30 SSCG steps. But when you use a fixed number of SSCG steps, we see that the error is getting bigger and bigger with an increasing as a sequence as a length. And this is also perfectly resembled then here on the plot here, where we use this dynamic stopping criteria and check how many steps on average do we spend during optimization. And we see there is usually fewer steps in optimization early in the sequence and ramping up, then up to a certain level, and then staying at a similar level up to a sequence length of A as a K, which shows like that we need more SSCG steps the later we are in the as a sequence. And then maybe as a small shameless advertisement from this side, we also set up a collab tutorial with the MesaNet where you can play around with some experiments we did in the first Mesa paper, but also now in the second MesaNet paper. And like here, especially thanks to Songling for writing all this GPO-based as a Triton code in a really fast way, such that everyone can try the MesaNet and play around with it. And with this, we are already at the end. Like, thanks all of you for attending. Floor is open for questions. And if anyone has any questions, wants to brainstorm about any follow-up as a project, please feel free to reach out.
Can I have a question?
Sure.
So last year, thank you for the talk. It was super interesting. Last year, Google DeepMind published this paper, Mixture of Depths, where they basically train a little router, which dynamically decides if all of the blocks of the model should be executed. And they show that sometimes you can save on compute by not running all of the blocks of the model, but instead stopping earlier or just skipping some of them. I was curious if this idea would be in any way applicable to your model. Like, do you think there is a potential for saving on compute by skipping some of the layers? Because the Mesa layer follows completely different principle than self-attention. So I'm just curious if you think this could work or not.
I think it's kind of an orthogonal approach. I mean, so what is interesting kind of that, I mean, you don't see it in these aggregated plots here, but there are really sequences which, so these are like average numbers of CG steps during the sequence. I think that yes, there's a data dependence on the compute that you will use in both of the methods, like in the mixture of depth and here this CG step, kind of dynamic CG step allocation. But I think they're somewhat orthogonal because, yeah. One interesting part, just one comment that we also might want to try in the future is, so one detail of the Mesa layer is that during training, you always assume, so this, yeah, doesn't really answer your question, but it kind of falls into the same category of test time compute. So what you can do basically is, so we train the MesaNet by assuming that it is at fixed point. And then this has, so when you do then the backpropagation, you assume that the forward, like this conjugate gradient method actually converged. And another thing that you could do is actually backpropagate through the solver. And therefore you could actually prompt the model telling it, we are going to give you X amount of steps during inference. So you could have like a special compute token in the sequence input. And therefore, a little bit maybe like the mixture of depth, tell the model, I mean, here you would actually tell it in the mixture of depth, I guess it's also trained for it and maybe penalizing like long depth. I don't know exactly what they do, but you could give like this token in the beginning saying you're going to use like, I don't know, maximum number 10 conjugate gradient steps, and then you could actually change your representations and the inputs to these layers such that 10 conjugate gradient steps for that representation gives you better convergence compared to not doing it and not training through this optimization process. But yeah, like I don't really know what you were thinking about combining these two, but indeed both methods somewhat. I don't know how they do it actually in mixture of steps, but both methods, of course. Like, how is it? Can they tell the model to use like more compute during test time, dynamically given like how much compute you want to apply? If so, then these methods are kind of similar by choosing like the salus epsilon, which controls this cost.
Cool, thank you. That's helpful. Thanks a lot.
I had a question that's kind of beyond the sort of standard benchmark. So transformers are really good at interpolation across their training data. For example, I don't know, write a business plan for a startup in the form of a Shakespeare sonnet, right? And like this, I suspect that this is kind of based off of the architecture of the transformer, where like it has this global weighted lookup mechanism, right? And so MesaNet is not a storing raw concept. Everything's compressed into these finite sized G and H matrices, right? And so this kind of the process of continual optimization and compression is going to smooth out the distinct and sharp details that you might need for that kind of juxtaposition. And so like I'm just wondering how you think about that, because like I'm thinking that like this is this kind of interpolation task is a late game synthesis problem, right? And MesaNet's strength is in the early game, right, where you're building something from the immediate context. But I don't know how you think about it. Like, is that the right way to think about it?
I think they're a bit as a mixed feelings. Of course, like there is a bit this task interpolation, like this task arithmetic, which you can do quite well in the transformers, and this probably quite close also to this interpolation regime. But to the other extent, like we also know that transformers are really quite as a sensitive to like token as a ordering as a syntax and so on, which is also probably a bias to this data weighted storing and as a retrieving mechanism. So there's probably like also quite some hope that like these more compression oriented architectures who have another inductive bias of how they compress alleviate a bit the problems we have over there. But of course, like there is this other view, like can we really use these task vectors then to do these things efficiently, especially in context learning, where you can really like use this task vector to do quite surprising things. But I think it's like, I cannot really answer the question. So I think it's from all views, like clever benchmarks and definitely more as needed, like not only for RNNs, but also in the transformer, because it's still really hard to disentangle, like what can a model really do? Where do we just benefit from the training data do we have? Can we really go out training distribution and benefit from this interpolation? So I think, especially me as more an eval kind of person, it's hard to answer without seeing empirically like how these things as a play out.
Okay, well, I have another thought. Like, wouldn't MesaNet be better at something like the ARC challenge than transformers, sort of a priori from inductive biases? Just because, I mean, that's essentially what it's designed to do, right? And you're building a locally optimal model of the data. You know, whereas transformers are, you know, finding patterns that are similar to what it saw during training. And so like, you know, an ARC is really designed to be sort of novel tasks. I don't know. Does that make sense?
I think it does. Like, so at least that was kind of the hope. I think that like the original motivation was really to find like a model that can do in context learning super well. I think the difficulties that we run into is really this long context. So whenever you try to do this over as many tokens and potentially like the ARC challenge to encode like one of these grids, you need a couple of hundred tokens, and then you quickly reach like the limits of that context, which could be fine if you are truly able to compress it in the state and then just learn from it. So you don't even need this long context. So I think there's this tension here between let's say latent inference, but it could be that you just need more context to do this. And yeah, we tried to analyze like the differences on other in context learning tasks. But yeah, like these are super interesting questions. Like I love the view that you have of that the Mesa layer and actually all other RNNs are supposedly compressing context. Like that would be great if that brings down perplexity. But it tends to be that I think a lot of language is recall. So the memorization view to some extent is for now the prevailing one, and memory is way more important than the compression part. That is like intuitively saying, like, I think the take-home message here for now. But yeah, we hope to, for example, through these hybrid models, I think there's a little bit of hope to at least use these models and hybrid models where you tend to combine these strengths. So you have like a couple of softmax layers that are costly, but you just need them because remembrance is so important. But then you have these other models which are actually potentially better for other parts of language modeling, especially when it comes maybe to in context learning or reasoning or things like that. So yeah, these are like the current hopes.
And also something to add here, which was interesting to see, like there are these really cool GPT-3 tasks, these few-shot learning tasks that are kind of underlooked in many of the recent papers. And like, for example, one is this cycle as a letters in as a word, where you just permute the order and you just swap over at the right and then you append it on the left, where you need to unpermute kind of the ordering. And the interesting thing is, like, if you look here on the comparison in this word scramble as a task, so MesaNet is doing really, really well here, also all the other recurrent models, and there is quite a gap to the transformer. And I think this is, generally, like this in context learning task can be of quite as different as a nature. For example, at translation, you need a lot of as a lookups where you need to relate words together, need to have a contextualized understanding, where transformers and attention mechanism is probably the better choice to do the task. But on the other hand, on this word scrabble, where you more need to learn the rules of the task from the few shot demonstration, these recurrent models seem to do really so well. So I think it's really like it would be interesting to run MesaNet on Arc, but I guess like we would need to scale it up by some order of as a magnitude more to get in a regime where we have the ability to do something. Because I saw someone else ask if we run already on Arc as a channel.
Yeah,
and I think.
Cool. Oh, so sorry. One last bit from me. So the other thing I was thinking about is like that. MesaNet is gonna have a fundamentally different type of response to RL post training than transformers do. Where the RL update is probably going to be adjusting the parameters that are governing the internal optimization process itself, right? And so, I'd expect it to like be very different, right? Where like I don't know, I'm thinking maybe that like in a transformer what RL post training is doing is they're like the primary learning target is the patterns of the correct final output. Whereas in MesaNet, it's more likely to impact the process of reaching a solution. Does that make sense?
Yeah. And like I think it's hard to say what happens in the RL phase, but I would love to see the finding that you're suggesting. But I think it's generally interesting to look what happens if you apply RL based on this model. Like, does this other cool line of work as a minimax 0-1, I think. They use a hybridization of linear attention and softmax models, but they're like scaled up model on RL with a bit of as a tricks on the RL side seems to work really well, and like also close the gap to quite many frontier models out there. So I think it's definitely also interesting, like what happens if you apply RL on these models? Are you able to overcome some of the limitations they have in long context modeling? Like, can you teach the model to separate like better which informations to save and to recall for later phases and so on. And I think that's generally an interesting avenue of as a research, like what as a signals or what changes do you need to apply to get these models to be better at long context. And especially if you look at these plots, like it would be cool to keep the gap that we have here with these linear models, but also enlarging again the advantage as we do a longer scale, that we can keep the advantage to the transformer. Because the question is also a bit like, how much does it really help here to have the gap at the beginning? Like, do we really gain something from it?
But what I love about this line of questioning is more to think about, like, I think a lot of these RNN models are motivated from their efficiency point of view, which is very important. But I think it's really interesting also to look into, and that was also the kind of motivation from the MesaNet, like not really targeting this and like optimizing for this memory point of view, approximating potentially softmax, but actually, you know, spending these flops that are like considerably slowing down the model to something useful, like to actually, as you said, like do better latent inference, compress more and so on, and actually be like a generally better sequence model than a transformer. So yeah, I love this, how you put your questions.
Yeah, no, I think that is like a super interesting line of research, is how they react differently to RL post training. Anyway, thank you.
I think there is one for Johannes. Someone in the chat asks, can you elaborate a bit more on the numerical stability of the CG Mesa layer, specifically the GLA computation?
So Songlin can answer that better.
I think you're
Oh, sorry,
muted.
I mute myself. I think for this iteration, you guys are using FP32 on TPUs for training. But FP32 is like matrix multiplication is like very inefficient, like in on GPUs. So we have to use like either we have to use low precision and tensor matrix multiplication to leverage the tensor cores. And I think in the very first beginning, I used BF16, and everything looks good. But when I do some debugging, and I found okay when the gamma term, which is like the forgetting factor, is like very near to 1. And I think like the overall relative error is like quite large, because like when the forgetting factor approach to 1, it makes the CG iteration more difficult to converge to the global optimal. And in such scenario, I found BF16 to be really bad. And then I start looking into like some other precision like FP16, and I found like FP16 is much better than BF16 in this CG iteration. Yeah, and so I highly do not recommend using BF16 for this CG iteration. And I think like by carefully handling these variables related to CG iteration, we do not need to use like TF32 for training, because like TF32 is still like about 1.5 to 2 times slower than FP16 machine application. And more importantly, they have the same precision, which means that you cannot have better precision when you're using the TF32 format. And we cannot use IP32 matrix multiplication for large scale training. So I think like a good workaround is like to use IP16 during training. And it should achieve very good performance. And I think like I'm still maintaining the kernel. And if you encounter any like NAND issue, because we all know that IP16 is very prone to this NAND issue. If you have any NAND issue, just come to me and I'll fix it. I'll fix it.
Yeah, like one thing which we have this under our abstract. We have this comment from our colleague that implemented the Triton kernel and looked at this in detail, which was that you shouldn't scream at your least square solver. And so what this basically means is we wrote this in the appendix. So when you have, as Song Lin said, the gamma term close to 0, and you actually scream at your language model, so you always use, let's say, the same token, what happens is, at least in the early layers, is that you load up this H matrix always with the same K. So your condition number gets really bad while the rank kind of stays constant, which is super bad for this convergence also. So what we basically did, so what you can do is what we also found out later. So if we would change something in the paper, I think this would be like the number 1 is that you should use a tokenizer which kind of eliminates these repeated, for example, like repeated tab tokens or repeated empty tokens that are happening a lot in like unfiltered text, such as the Slim Pyjama, and especially in code. So if you use like better tokenizer, I think that there should be a little bit less problems. But so we had these problems because we didn't really understand that a tokenizer, for example, could solve it back when we were starting. And so what we did is also we restrict the gamma terms to be a value very close to 1, so something like 999. And though this effectively introduces a strict upper bound of how large your H matrix can grow. And this helps also a lot with convergence. So yeah, just another comment. So if you run into problems, maybe restrict the size of your gamma to be very close, but not exactly 1. So we also described this in the appendix if you want to have a look. So this is another way to stabilize a bit the numerics here. But just an interesting fact, like I was So we, of course, when we implemented this, we had like a lot of worries about the numerics, because like, yeah, just an interesting fact, during like a forward push of a layer for MesaNet that this has like around 1B, I don't know, you're solving a couple of millions of systems of equation in one forward pass and back propagating through it. So it's really like I don't know, from that perspective, like a special neural network.
Are there any other questions?
Did you try running MesaNet in a loop like latent reasoning? No, we did not yet. Like, of course, like there are like many interesting extensions one can do, and like comparing with kind of similar to the question before, like with can you exit the layers earlier? I think those are all kind of orthogonal like research as a questions to look at, and also like with this latent as a reasoning kind of stuff.
Yeah, I think I can ask several questions. So first off, like MesaNet is still working with linear associative memory, and we all know that there are some recent model using nonlinear associative memory like Titans and Titan training layer and stuff like that. And I think like there's a recent paper called TTT downright, and they show the nonlinear associative memory is like way more effective than linear associative memory. Do you think like the first question is like, do you think the linear associative the inherent linear associative memory would like restrict the Mesa layer? And the second is like, do you think because like for Mesa layer is still like use a fixed size, state size. Do you think like for example, there's a recent work trying to extend DataNet to its softmax version. I think there is a paper called the data former, and do you think there's any way to extend the Mesa layer to its like softmax version so you can have exponential memory capacity?
I think we should look at the details. I hope. I really don't know the details, but it would be great. I think coming a little bit back to the evaluation side, like I think it would be very interesting to know what you want to kind of do with these models, because somewhat the softmax. So one of my kind of take-home messages from this paper is a bit like softmax. Like if so, you can have tasks where you cannot beat softmax, right? So there are like classic key value association tasks. For example, also these ruler benchmarks and so on, these NIA benchmarks that you can construct always a setting where you need softmax. So you, with finite kind of memory where you don't store any, like everything, you will always lose against softmax, I think. I mean, potentially they are a little like given the kind of limited compute that you are kind of doing with softmax. I mean, it's a lot, so it grows linearly, but it's kind of given that it's actually quite efficient, I think. Like the operations that you do with a couple of vectors that you have is yeah, pretty rudimentary. So yeah, I think it really boils down to the evaluation side, what kind of model you want to design. If you can like extend, let's say, the memory capacity of MesaNet by doing maybe a little bit more flops, it's great. But yeah, I think I don't know, like I'm a little bit more in this camp of trying to improve like other capabilities versus improving the memory side. But
Yes. So I think there is a recent trend trying to bring those new technique from the linear attention literature back to the softmax attention literature. Like we play around with like a dynamic data dependent forgetting gate, and there's a paper called forgetting transformer, essentially leveraging this idea and put a softmax back and to basically it's like a member 2 plus softmax, and it has a very good performance. And previously I also had the archive paper called path attention. So basically it's like I use the attention logic computation of DataNet and have a softmax operator to wrap it so we can have like exponential memory capacity. And yeah, I think this is also a very interesting direction, whether you can leverage this like more advanced processing of this QKV attention logic and computation, and to make it to make a more expressive softmax attention. I think like maybe the simplest way to do it with MesaNet is that so we have the Q star term, which is like the matrix inverse multiplied by the original query vector, and if we directly feed this Q star term into a say flash attention kernel, we can have this is like the most simplest like the softmax extension of the MesaNet. Do you think this kind of like enhancement would like improve the transformer model itself?
I think so, right? I mean, just from a computational point, you can just do way more interesting things. So, I mean, you should gate more. The question is, of course, like a bit for all these flops that you spend, what do you gain in the end? Like, so maybe spending these flops on MLP layers or something will give you more and other benchmarks. But yeah, I think it's like a cool idea.
Yeah. And yeah, I think like many people and many maybe like say industrial folks care about like some fixed state size token mixing layer or sequence mixing layer, because this is really matter to those like real world deployment to do efficient inference. Yeah, and do you think like with a fixed amount of state size, what do you think like how do you think of this like mathematically optimal linear associative memory versus those nonlinear associative memory, where they could use the fixed state size to have more memory capacity?
It's hard to say. I think you have a better take on this.
I think so. I think this is mostly important also for like extremely long reasoning tasks and so on, right? So where you really have, I don't know, 16K rollouts and your memory and compute requirements for softmax really go in a regime that you don't want to spend. I don't know. I think people I don't know, like I think for now people have been just optimizing softmax much more and go like, yeah, there's this tension of just approximating maybe softmax, which also is pretty fast for the rollout length that you want. I think that one cool comment about this RL, like using RL to kind of fine tune these finite state networks, you could really get fundamentally different reasoning chains because the model kind of knows that it has finite memory. So it could maybe like before it actually kind of lose its memory, understand that it kind of needs to maybe spill out a couple of tokens that it then reads back again into its context, right? So you could imagine this RNN, when you train it on reasoning, actually outputting like a summary of some of the past, and actually then picking up that summary, actually recompressing the sequence that it's. So I mean, this would be like a really crazy cool emergent phenomenon, really, that the RNN through the RL pipeline kind of understands, okay, I have finite memory. Whenever my memory ends, my performance drops a lot on these chain of thought based reasoning tasks, and potentially I just like now it's kind of saying, maybe I need to go back there. So there are these R tokens, maybe for RNNs, there's these summary tokens, and you start like compressing a bit your sequence that you read, and therefore remember everything that you need to solve the task. Like, this would be really cool. Maybe that happens, like.
Yeah.
And is much more efficient, right? I mean, could be.
Yeah, thank you for your answer. And there is another question in the chat. What is the expressivity of MesaNet in terms of complexity class, TC0 or NC1?
You know better, but it's definitely not better than other models like DeltaNet or gated DeltaNet or so.
I think this is a very great question. I've discussed this question with several theory friends, and we conclude that like a MesaNet is still within the TC0 complexity class. Where DeltaNet could be beyond NTC0, which is a very interesting phenomenon, because in terms of like the online learning objective, MesaNet is more expressive than DeltaNet for sure. But in terms of like this recurrent update, DeltaNet appears to be more expressive than MesaNet in terms of this computation complexity. Yeah, I think like the reason
we have like a small appendix where it's kind of it was kind of a desperate thought that one of our theoreticians looks at it and like finds a way to, I don't know, solve at least like parity or something with the MesaNet. But so I think you can kind of force the MesaNet like just mathematically to be like gated linear self-attention by having like a very large lambda. So the Q star is very, very close to the Q. And then you can do like this trick of introducing, I think that comes more from the state space model literature or RNN literature. You can provide like gamma terms that are X-dependent, which introduce like negative eigenvalues of this transition matrix. And then you can solve at least parity. And you can also do it with Mesa, by just making Q star equal to Q and actually introducing like negative eigenvalues by having negative gamma terms. So this works, but it kind of is working against the MesaNet because the Q star is the same as Q. So and here we hope to have the magic of the MesaNet. So
yeah. So you can do some restriction to make MesaNet more like a GLA model with selective gating turn. But I would also like to comment that so even gating linear attention, this sort of like linear recurrent model with diagonal transition matrix, even if they have lective eigenvalues, they're still within the class of TC0. Although they can do parity tracking, but parity tracking is entirely a TC0 complexity, so it's not it has I don't think it has much thing to do with like NC1. And
yes.
Yeah, and also there's like a quick proof why MesaNet is within the class of TC0. So so in the first we can look into the computation graph. So in the first stage we calculate two stages, both of which use like a diagonal transition matrix. So the stage computation are within TC0, and then for each position we need to solve a matrix inverse. Because the height dimension is fixed, then this matrix inverse complexity does not grow with respect to the sequenceless. So in this sense, MesaNet is not a NC1 complexity model.
Yes. Yeah, interesting.
Yeah, very interesting.
So we need to grow the size of the net, of the Mesa layer.
Are there any questions?
I can throw in a few more thoughts on RL. So like the other kind of interesting aspect of RL post-training for these models is that, you know, you can try to manipulate what is learnable during the RL process. So like, you know, it could be just the regularization matrix, which is, I think, controlling the stability and behavior of the linsolve optimization. And so then, you know, that could potentially fine-tune it to make the internal solver more suited for the kind of problems that it's facing. Or, you know, alternatively, you could like make the input gate more selective. I mean, there's a lot of possibilities. Anyway, just wanted to throw that out. If you have any.
Yeah, I think that also just generally fine-tuning the model, like these things are super interesting, because like based on that, on these toy models, like, so if you have these optimizers, let's say in your network, like either you really implemented them in a transformer or something, there are like a couple of weights that are super important for out of distribution generalization. So there are a couple of weights which are, as you said, like even not if you bake in the Mesa layer per se, but just in generally, like if you have, let's say, this Mesa optimization in your network, a couple of weights are super important. For example, controlling like learning rates, controlling like these kind of things, regularization term, exactly what you said. And so if you want to do out of distribution generalization, so you train on a family of tasks and then you really change that, only changing these couple of parameters really efficiently make your model like vastly generalized out of distribution, like after fine-tuning. So the fine-tuning term, as you said, like really carefully, like investigating maybe which parameters are important to fine-tune for a task with RL or with just supervised fine-tuning. Yeah, it's super interesting, and like let's hope there's hope, as you mentioned, that this is actually true. Like, yeah.
Okay, I think we are already time up, and thank you again for the very amazing talk.
Thank you.
Thanks a lot.
I'll stop the recording.